So I think that we are ready to start. Thank you everyone for joining one more day to this lecture on heterogeneous systems. Today we are going to keep talking about GPU programming, and in particular we are going to introduce the memory hierarchy and the different memory spaces that the GPU threads can have access to. Before we go into the explanations corresponding to today's lecture, I want to very briefly summarize what we discussed in the previous meeting when we started talking about GPU programming. Recall that I recommended you a couple of readings. The first one is this textbook, Programming Massively Parallel Processors by Dr. Kirk and Professor Wen-Mei-Hu. And the second one, it's an important one. It's the GPU programming guide, where you have all documentation that is needed to really master and command the programming of NVIDIA GPUs. Okay, so recall that when we talk about GPU computing, we normally use what we call the accelerator model, in which the GPU is seen as a loosely coupled accelerator, where the host CPU offloads some computation. And we typically have 5 steps, including allocation and deallocation of data in the GPU memory. But in this slide, we are focusing only, assuming that we have allocated the data, we are focusing only on the 3 key steps. The first one is the data transfer from the input data, from the CPU memory to the GPU memory. After that, the CPU will launch the computation on the GPU cores. This is step 2. And then in step 3, we retrieve results from the GPU memory to the CPU memory. So if we take a look at the traditional structure of a heterogeneous program using CPU threads and GPU kernels, what we will normally do is computing sequential or modestly parallel sections of code on the CPU side and massively parallel sections on the GPU. So the way that we are going to execute threads in our program is going to be something similar to this. In the very beginning, we will have only execution on a single thread or just a small number of threads on the host, on the CPU. And at some point, we will launch, this main thread will launch one kernel to execute on the device. And this kernel usually will have many more threads, typically thousands or even millions of threads. And we cluster these threads in some way. We group the threads in some way. So the groups that we form with the whole grid of threads are called thread blocks, as you may remember. And this is what we use in this part of the kernel code, that is the execution configuration, where we define the number of thread blocks and the number of threads that we launch onto the GPU. And after that, the kernel will terminate, the host gets notified in some way, and maybe we can continue the doing some computation, some execution on the host, because, for example, the host is going to apply some results coming from the kernel into later computations. And at some point, we may launch another kernel, which might be the same one, if this is some sort of iterative algorithm, or it might be a completely different kernel. And continuing with the program structure, we are going to use these function prototypes. Usually, you guys are familiar with C programming or C++ programming. You know that this is the normal declaration of a function in C, function that is going to execute on the CPU. When it comes to declare functions, the kernels that run on the GPU, the syntax is very similar, but we add this global qualifier to make sure that the compiler understands that this is a kernel that will run on the GPU. And in the main function of our program, recall this runs on the host side, we first allocate memory using CUDA malloc with a very similar syntax to malloc in C. We have here the pointer to the specific memory area in the GPU memory and the number of bytes that we allocate. After that, we will transfer from the host to the device from some array in the main memory of the CPU to the global memory of the GPU, please notice that we need to do some kind of double allocation, right? We first need to allocate, for example, using malloc, thishin in the main memory, then we use CUDA malloc to allocate this din in the GPU memory. Then we decide the execution configuration. This is going to be dependent on the size of the data sets that we are processing. And then we call the kernel. We execute, we launch the kernel by using this syntax here. Here in the middle, we will have the execution configuration, number of blocks and number of threads, and you may remember, and the arguments of the kernel call. And finally, when the kernel terminates, we will likely transfer results from the device memory or the global memory to the main memory using, again, CUDA main copy, but in this case, in the opposite direction. And this sequence might be repeated multiple times, as I said, for the same kernel or different kernels. Yeah, this is the, again, the declaration of the kernel, and what today we are going to talk. We are going to talk today about the different memory spaces that we have, that we can use from within the kernel, such as registers or shared memory. And we will also introduce today these sync threads, which is a synchronization function or API that we use to synchronize threads that are running together on the same core, and they belong to the same thread block. And these are the syntax for different constructs that you need to use when programming and a GPU and allocating memory, copying, launching kernel, etc., etc. Remember that our first example was this vector addition. It's very simple computation in which we launch as many threads as input elements we have in our input arrays, and then we have each thread computing each of these each of these element-wise additions. The whole set of threads is called a grid. And we need to have a way of partitioning this grid in order to assign the threads to GPU cores, because in the end, as you remember, and you will see again in one of our slides, the GPU is composed by multiple cores, and we need to decide in some way, or the scheduler that the GPU has internally will have to decide how to assign threads to different GPU cores. And to do that, we define the thread blocks, or simply blocks. So for example, these 4 threads will be block 0, these other four threads will be block 1, block 2, block 3, and so on. And this way, this block 0 computes this part of the whole computation, in this case, the vector addition. This is for block 1, block 2, and block 3. And now, when we launch the kernel, the GPU hardware already knows how many blocks and how many threads per block we are launching. There will be a thread block scheduler that takes the next block to execute and places it into some GPU core that has some available space for the thread block to run. This is the vector addition example that we saw the other day as our first GPU programming example. Recall that here we are allocating memory on the device side, on the global memory for arrays, input arrays A and B, and for output array C. Then we copy from one array A and one array B that are in main memory and previously allocated and initializing in the main function. For example, we copy these two to AD and BD, which are the pointers to the global memory of the GPU. And then when the computation finishes, we do exactly the same thing, but in the opposite direction. And finally, we may want to deallocate the arrays in GPU memory. And remember that to launch the computation on the GPU, we first need to define the number of threads per block. In this case, we use 512, and the number of blocks. What we normally do is dividing the total size of the inputs by the number of threads per block, and this will give us the number of blocks. And here is the syntax for the vector addition kernel. In some cases, as you may remember, actually in the majority of cases, as you may remember, the number of, so the total size of the input is not going to be a multiple of the number of threads per block. So we will have to round up the number of blocks that we use. We can use this expression, for example, to obtain the ceiling of this division, n divided by the number of threads per block. And the only thing that we will have to change in the kernel code, recall that this is the kernel code, and we define this index I using the block dimension, the block index, and the thread index for all the individual threads to index the specific elements in the input and output arrays that they are going to operate on. And then performing the addition, in this case, the vector addition. The only thing that we have to add to this kernel when we have to check the boundary conditions is something like this. It's like, okay, my index is I, but I want to make sure that the one particular thread I, belongs to the region of threads that are really going to process, because they have some elements waiting for them to do the computation, right? So that's why we have to check the boundaries here. There is not so much complexity. You also may remember that we were talking about how to index the threads and memory access. Actually, in the previous slide, you have already seen how to index a one-dimensional array using one-dimensional thread blocks and one-dimensional grid. And here we have another example where we do the same for an image, right? So remember, images are 2D data structures, and if we want to access one specific element, we need to know what's the row and the column. For example, this element here is in row 0 and column 1. This element, this pixel here, is in row 1, column 2. But the truth is that even though that's a two-dimensional data structure, these pixels are stored in memory in a linear manner, because in the end, memory is just a linear array. And we use a row major layout. In the row major layout, we store one row after the other. So these pixels here in memory correspond to rows 0. These pixels correspond to row 1. Here we have row 2, and so on. So if in the end, from the beginning of one row to the beginning of the next row, there is a certain stride, which is the width of the image in this case. And this element here, remember, this was element, this pixel here is a pixel 0, 1. So this pixel here actually resides in this address in the memory, in the global memory in the case of a GPU. And this is another example. And then we also talk about how to index and access memory when we use two-dimensional grids and two-dimensional blocks. Remember that we can also have 3D grids and blocks. It's essentially the same way of accessing. If you understand how to do it for 1D and 2D blocks, you will know how to do it for 3D as well. Here in the when it comes to indexing in a 2D grid, we have to take into account the dimensions of the grid in number of thread blocks. So this is the number of thread blocks in the X direction. This is the number of thread blocks in the grid in the Y direction. So in total here we have 1, 2, 3, 4. So grid dim X is 4, and here it's 1, 2, 3, 4. Grid dim Y is also 4. And this particular block that we assign here for the computation of these 4 pixels, in the end, notice that what we are doing is partitioning the whole image into different squares or different tiles that are each of them assigned to a different thread block, right? So this is assigned to thread block 0, 0. This here is assigned to thread block 2, 1, block index X equal 2, block index Y equal 1. And then internally, what we will typically do is assigning each of the individual data elements, pixels, to individual threads. So for example, this one here, to thread index X1 and thread index Y0. And if we want to access one particular element in this two-dimensional organization, we need to obtain the row and the column where the particular pixel, in this case, resides. So we know that this pixel here, for example, it's in 1, 0, 1, 2, 3, row 3, and column 0, 1, column 1. And the way that we obtain in our CUDA code the row and the column where this pixel is located is by using the block index Y, dim index Y, so block dimension Y and thread index Y as well, to obtain the specific row where the pixel resides. And for the column, we do the same, but in this case, in the X dimension, block index X, block dimension X, thread index X, to obtain this the column 1 of this pixel here. And now, after summarizing the previous lecture quite quickly, let me start talking about the contents of today's lecture, which are the GPU memories. We are going to talk about the GPU memories from the hardware. Well, we will see how they look from the hardware or architecture point of view, and we will also talk about how they are handled by the threads, or how they are used by threads when we are writing GPU programs, right? After introducing the different types of memories, we are going to focus on, let's say, the first memory that we have to learn how to use for optimization, which is the shared memory, which is a on-chip scratchpad memory, as you will see. You may remember this layout of the NVIDIA A100 GPU, and already in this layout you can identify at least 2 memory spaces. So first, we have the global memory. You may remember this architecture, and this specific GPU is using HBM2 memory. So here we have 3 stacks of HBM2 memory that are accessed using 2 memory controllers. On the right-hand side, we have exactly the same, another 3 stacks of HBM2 and 2 memory controllers. And here in the middle, we have these 2 large chunks of L2 memory, of L2 cache, right? It's especially interesting in this A100 architecture, the fact that the size of the L2 cache has significantly increased, around 6-7 times larger cache, L2 cache, than in the previous architecture, Turing and also Volta architecture. So this is something quite interesting and probably related to the needs of the most important workloads these days. And if we go to the internals of a GPU core, besides the instruction caches that you can see here, L1 and L2, on-chip storage for operands. So we can see in each of these different 4 parts of the SM, we have some registers. This is a register file. Recall that GPUs are essentially a SIMD architecture, and you remember in SIMD architectures we use vector registers, right? So these are essentially these vector registers that are and this register file is partitioned into multiple chunks or groups of registers that are assigned to the different threads that run on this core. So this is the register file here. Here we have another part of the register file. And then we can also find in this SM, in this GPU core, more memory spaces, like, for example, this blue area here, that is the L1 data cache and shared memory. In the particular case of the A100 GPU, this is 192 kilobytes, both together, L1 and shared memory, 192 kilobytes per core. This has been changing, normally increasing over time from the 16 kilobytes that the first CUDA capable generation had to these 192. And why is this, the size of this cache and this shared memory, increasing? Because they are very useful and to alleviate the long latency of access to the global memory. One other comment here even though it's not so much relevant from the programming point of view, is that these two, the L1 and the shared memory, normally are exactly the same memory array, the same memory organization. It's a decision of, so it's either they are both partitioned statically, depending on the specific architecture generation, either partitioned statically, or it's possible to do some reconfiguration. And in some architectures, I think that the A100 is one case. The programmer or the compiler can decide how much of these, in this case, 192 kilobytes we spend on L1, which is a pure hardware cache, or shared memory, which is a kind of software cache or a scratchpad memory that is controlled by the programmer. And here we can take a closer look, and also, you know, it's a more simplified representation where we can even see the different memory spaces more clear. We have different SMs, GPU cores. We have different SIMD lanes, as you may remember, and next to them, close to them, we have the register file that is very fast to access, typically one cycle. And also on chip, in each of these GPU cores, we find the L1 cache and we find the shared memory. This is also very fast access, almost as fast as the registers. And we also have another space that is called the constant cache that we will typically use in our programs to store constant data. And it results in quite good performance and efficient access when all threads of the warp access the same values from the constant cache. But if we cannot find the data either in our shared memory or L1 or constant cache or registers, then we will have to go somewhere else, right? We will have to go off chip to the global memory. And because the global memory is off chip and we usually access it through the memory bus, that's normally kind of a narrow avenue where the data needs to go through, the latency is normally much longer. As you can see, it's essentially 2 orders of magnitude longer latency. And actually, the very first generation of NVIDIA GPUs back in 2007, 2006, there was only global memory. So if you could not manage to read your data from shared memory or from the L1, you would always need to go to global memory. Fortunately, later generations, starting from the Fermi architecture in 2010, started to introduce a level 2 cache, an L2 cache that is much faster to access. Actually, it's in the order of tens of cycles to access this L2 cache. But the memory hierarchy continues evolving over time and generation after generation. Here you can see this is not really so much relevant for today's lecture, but I wanted to show you this innovation from the recent A100 architecture. So today we are going to talk about how to use the shared memory, which is this on-chip scratchpad that we have in every GPU core. And the normal way of using this shared memory, as you will see, is keeping in shared memory data that is going to be frequently used, and it's coming from global memory. So what we normally do is reading some chunk of data or some tile of data from the global memory and putting it into the shared memory. And if we want to do this operation, what we essentially need to do is to vision one, load to global memory, bring data from global memory. We will temporarily store this data in registers, and then we need another instruction, in this case, a write to shared memory, to move the data from the register to the shared memory. And that's essentially what you can see here. First, a load from global memory, then a store so load from global memory, and then we bring the data to the register file, and then we store in shared memory. And here you can see one more operation, but this because this figure also explains how the tensor cores access data from shared memory. But regarding let's say the data flow that we are interested in right now is first this load from global memory, then one store to shared memory from the register file. Good thing in the A100 is that it allows us to copy data directly from L2 or from DRAM global memory to the scratch pad, to the shared memory. So as you can see here, we have this async copy operation that directly brings the data from L2 to the shared memory without having to go through the L1 and the register file. So we are bypassing L1 and register file and probably doing this operation in a shorter latency and more efficiently and better performance in the end. Okay, so after explaining that and briefly introducing, how the different memory spaces look from the hardware point of view, let's start talking about how to use these different spaces, these different memory spaces from the software point of view. Here you can see the different ways of declaring variables internally inside our GPU kernels. And one thing that we can do for sure is using automatic variables, like for example, this local bar. Whenever we declare one variable this way, this variable will be placed by the compiler in a register. And the scope of this variable is a single thread. So if I'm using automatic variables in my GPU code for each particular thread, the compiler is going to allocate registers for the threads to store the local variables in these registers. And the data that we store in this register will live for the lifetime of the thread. In some other cases, we may declare, instead of declaring only variables, we may declare arrays, complete arrays. In this case, we do here an array of size n. So normally the compiler is going to place these local arrays in some reserved space in global memory, in the device memory. But this reserved space is only accessible by a single thread. Recent versions of the compiler try to avoid this type of allocation, because in the end, whenever the thread needs to use some data residing in this local array, it will have to go to the global memory. And you remember, it's a long latency operation. And we want to avoid that as much as possible. Of course, we have L2, we have L1 that can probably keep this data from the local array for some time and allow the thread to access data with shorter latency. But what the compiler tries to do in more recent versions of the compiler, as far as I know, is to store this array in registers if it's possible. And there are available registers, there are enough registers. This is normally possible when this n, the size of the array, is a constant, and this constant is known at compile time, because this way, okay, this n, for example, is 20, the compiler can say, okay, I'm going to reserve 20 registers per thread to store this local array. It's one potential way that the compiler can optimize the access. We also have the shared memory that we declare this way. This array shared bar is going to be stored in the shared memory that each of the GPU cores has. And the shared memory, it's called shared for a reason. And the reason is that whatever we allocate with this shared qualifier will be accessible and common to all threads in one block. So I may have 128 threads in each block, but when I declare one variable, one array using this shared qualifier, all threads of the block will be able to access this array in shared memory. In other cases, we don't want to allocate in shared memory. We want to directly allocate in global memory. In that case, we will use this qualifier device. If we do device in global bar, we are going to place this variable in the global memory. But yeah, that will depend on your style of programming. You would probably use more this CUDA malloc whenever you want to allocate something in global memory, right? And then you will pass the pointer of the device memory of the global memory to the kernel, and the kernel can, the threads in the kernel can access whatever data they need from global memory. There is also a constant memory. As you can see, this constant memory is actually also located in the global memory, in the device memory. The only thing is that the GPU cores, as I said before, have some small constant cache where we can allocate parts of these arrays in constant memory for faster access. Yeah, and also as you can read here, this device is optional when it comes to declaring shared or constant memory. So we normally don't use this device here. And this is, yeah, I think this is a very clear picture of how the memory hierarchy is organized in CUDA programs. On the left, you can see the host. On the right, you see the grid composed by many, many threads. In this particular picture, we see two blocks, block 0, 0 and block 1, 0. And these blocks are each composed of two threads, thread 0, 0, 1, 0, and this is also 0, 0 and 1, 0. And as you can see, each individual thread has access to its own registers. This thread has access to this register, this thread has access to these registers, and so on, right? So each thread has access to their own registers individually. And if they want to share data or communicate in some way, they can use the shared memory space, which is also like visible to all the threads belonging to the block. So for this block 0, 0, you can use this piece of shared memory. For this other block, you will have some other space in shared memory, which may be in the same GPU, in the same GPU core, or maybe in a different GPU core. One comment here about the ability of accessing registers from, registers from each thread is that yeah, a few years back, NVIDIA introduced in their SDK a new type of operations that are called warp operations that allow, actually called warp shuffle operations that actually allow threads to access data that resides in the registers of other threads. This is kind of interesting feature, an interesting set of functions or operators, because it can allow you to, so it can allow, yeah, allow you to have threads in the same warp, because this only works for threads that belong, 32 threads that belong to the same warp. It allows this thread to share data that resides in different registers that are initially assigned to each of the individual threads, and this saves some latency of access to shared memory, which was the only way of sharing data across threads, even inside the same warp in older generations of CUDA. Here in the bottom, you can see the global memory and the constant memory. Both are actually in the same memory space. Both are the device memory, the DRAM of the GPU, and they are accessible from the host. So remember that we use this CUDA main copy. When we use CUDA main copy, what we have is the host sending some array to this global memory, and we have similar construct for the host to write in the whatever we declare as constant memory. Okay, let's go in more detail about how to use the shared memory, this scratchpad or software cache that we can use in our programs. We are going to use this simple example where we are applying some simple, well, relatively simple computation on an image. What we are doing in this short code here is applying a Gaussian filtering that can be used to equalize the values of the pixels in the image and somehow soften how the image looks. So if you look at this code and see what this code is doing, what we are essentially doing for each individual pixel of the image located in some row and column, what we are doing is this kind of convolution where we apply some filter, in this case, this Gauss filter, we apply it on top of each pixel. And the overall computation is doing here for each individual pixel is multiplying the surrounding pixels by the corresponding element of the filter and adding them all. And this sum value is the value that we will store in this pixel of the output image, right? And now, if you think about, let me very quickly use, so if you think about this, what we normally, in this kind of operation, what we are typically going to do is assigning one thread to this pixel, and this thread will have to access all these pixels surrounding the assigned pixel, and then perform the corresponding computation, the element of the filter multiplied by the value of this pixel, and then this one, and then this one, this one, this one, and so on, and we accumulate them all, right? And as I said, we are going to assign one thread per pixel here, so we will also have another thread performing similar computation for this pixel here. And actually, if you look at this, the surrounding window of size 3 by 3 are these 9 pixels that I'm surrounding with the square. So the interesting observation is that there is a lot of data reuse. Why do I say there is a lot of data reuse? Because all these 6 pixels that we have in the middle are accessed by both this thread here and this thread here. So this is data reuse. And when we have data reuse, what we want to do is, we have an opportunity to have more efficient access to memory. You guys are familiar with CPU architecture, and you know that there we have caches, and the goal of the caches is to exploit spatial and temporal locality, right? So here we have that. We have a locality, and we have the possibility of using some faster memory where we store some data for some time, and we have faster access to this memory. And this memory, in the case of the GPUs, is the shared memory. So what we are going to do, and we are going to assume here that we are using 4 by 4 thread blocks. So we will have one thread block operating on this part of the image. So one thread here, another thread here, another thread here, and another thread here. And because all these threads are sharing a lot of pixels that they need to access from the image, what we are going to do is assigning one whole tile of data of the image to this thread block, 4 by 4 thread block, and we will load all these things into the shared memory for these 4 threads to have a faster access to the corresponding pixels. And this is more or less how our code is going to look. We first have to declare the shared memory. Remember this shared qualifier. We are declaring some array called L data that has this size. Essentially, L size plus 2 is in 4 in this figure is this, and L size plus 4 is this, right? And then we load the tile into shared memory. To do that, we will normally have threads. These 4 threads reading the whole tile and loading it into shared memory. We are going to see one example later, but I don't want to spend time on that right now. I want to first focus on the structure of the program, right? Declaration of the array in shared memory, then we load the tile in shared memory, accessing global memory, and reading from global memory and writing into shared memory. And then we will have to synchronize these threads. Why is that? Because, typical number of threads that we are going to have in a thread block is not 4, as in this one, right? We may have something like 64 or 128 or 512. So that's a lot of threads. And 512 threads are essentially multiple warps. Actually, 512 is 16 warps of 32 threads. And as you know, you may remember from or lecture about the GPU architecture and SIMD processors, these warps execute in lockstep. So every 32 threads execute together. And we know that they execute together always, as long as possible. Of course, they may diverge, as you may remember. But for example, when it comes to access global memory, if it's possible, we want them to access together and bring the data all together and write it, in this case, to shared memory all together, because this way it's going to be more efficient. But this happens among the threads that are in the same warp. If we have 512 threads per block, this means that we have 16 warps in this block, in this thread block. So all 16 warps and the instructions for all these 16 warps will be scheduled at different cycles. So then they will finish, for example, this operation here, loading the tile into shared memory, they will finish it at different cycles. So at some point in cycle 0, we will have warp 0 reaching to this point, and then a few cycles later, we will have warp 1, and then so on. If we don't use this sync thread, the problem is that parts of the tile will be loaded, and other parts of the tile won't be loaded when some particular warp, for example, warp 0, starts computing here. So if we want to make sure that all warps of the block were done with this load tile into shared memory, we need to synchronize. And we can talk a little bit more about sync threads. As I said, synchronizes all threads in a block. Once all threads in a block have reached this point, this sync thread execution resumes normally. And why do we do that? To avoid these data hazards that I just explained, right? So when we use this L data that has been allocated in shared memory inside this inner loop, we want to make sure that all the data coming, or the whole tile coming from global memory, is already stored in the shared memory. And we are going to see one more example about how to do blocking and tiling. But yeah, let me remind you that this is kind of a very common optimization in when using on-chip memory. Like blocking, or also called tiling, consists of dividing the computation on arrays into multiple chunks and loading each chunk into some on-chip memory, for example, a cache to have faster access to this cache. Here we talk about cache in a generic manner, meaning cache, whatever on-chip memory we have in our system that can be accessed at shorter latency than going to the main memory or to the global memory, right? And so it may be a hardware cache, it might be a scratchpad as well. And the good thing is that we also avoid cache conflicts when computing on different chunks. We focus on one chunk, we forget about the rest of the image, or we forget about the rest of the input. We only work on that, and then we make better use of the cache and hit more, and in the end perform faster execution. So the idea of tiling and blocking is dividing the working set into pieces that fit the on-chip memory space, one cache or one scratchpad, as I said. And first of all, I want to show you one example for CPUs, but in the end, as you will see in later slides, it's all very similar to in GPUs as well. This is the example for a CPU, a matrix multiplication. Remember, in a matrix multiplication, we have two input matrices, A and B, and we produce an output matrix, C. So when we want to compute each of the individual elements of the output matrix, what we have to do is reading one whole row from matrix A, one whole column from matrix B. And we can write some naive code for these to implement this matrix multiplication, and we can write something like this. Notice that this most external loop, we go row by row, then we go column by column, computing, because it's a CPU execution, right? So we have a single thread of execution that is going over all elements of the all elements ij of the output matrix C, and then in this inner loop we will have the thread going through all the elements of matrix A, of this row of matrix A, and all the elements of this column of matrix B. And the problem, the performance problem or the bottleneck in this particular code is mainly due to the access to matrix B. And why is that? Because remember that matrices are stored in a row major layout in memory. So all these different elements that belong to the same column of matrix B in reality are in different cache lines. So every time that we want the thread access one new element of this column of B, we will have a cache miss, right? And that's going to hurt our performance. So in order to achieve higher performance, we can do this tiling in the cache of the CPU, or also, as I said, we could do it in the scratchpad memory of a GPU or the register file. We are going to talk soon about that. And by doing so, we are going to have faster access because we will hit much more frequently in the cache. So essentially, we divide the output into tiles, and we start computing tile by tile. So if we want to compute the elements that belong to this tile, we will have to first load this tile into the cache, and also this other tile from B into the cache, and then we can compute on them. And then after we are done with the computations corresponding to the, let's say, partial columns that belong to this tile here and the partial rows that belong to this tile here, we can go to the next tiles in A and B and continue the computation. And here is how the code looks after performing this optimization. We are going to have some function that is essentially a matrix multiplication. These multiplied tiles is essentially a matrix multiplication of the small submatrices or tiles in which we are dividing our matrices A, B, and C. So we would first multiply this matrix here by this matrix here and obtain some partial results that we store somewhere in matrix C. Then we load into the cache this matrix here and this matrix here or submatrix here, multiply them and continue accumulating. And that's actually done, let's say, transparently in a CPU, because there we have hardware managed caches, so we don't really have to explicitly, the programmer doesn't need to explicitly move the tiles to the cache. The hardware is going to do that for us. And if you want to learn more about how caches work, especially on CPUs, you can watch this lecture by Professor Mutlu delivered in the past spring semester. But now let's continue talking about GPUs. Now we have introduced the concept of tiling, and we want to do an efficient matrix multiplication on a GPU. So again, we have our matrices A, B, and C, and again, in a similar way as we did for the example of the Gauss filtering, we are going to assign one thread per element. So we will have one thread here, one thread here, one thread here, and also here, and here, and here, and so on for the individual elements of the output matrix C. Let me find again the arrow. Okay, so if we want this thread compute this element of matrix C, we need, as you know, this thread read all this row of A and all this column of B, right? That's the way that we are going to assign the computation to threads. And this is our, let's say, naive GPU implementation of the matrix multiplication kernel. Looks like this. First of all, for each individual thread, index X, Y, in each thread block index X, Y, we compute row and column that we are going to access in the matrix, each of these elements in the output matrix C. We compute the row and the column the same way as we have seen before for the image processing example. And then we go to the inner loop. Remember that if you compare this to the serial CPU code that we have just seen a couple of slides ago, you will see that the only difference is in that we don't have the two outer loops here, because we don't have a single thread, we have multiple threads, and we launch as many threads as elements we have in the output matrix C. And this way, each thread just needs to compute this inner loop where we access element by element in the row of A, and element by element in the column of B. And then we accumulate, and finally we store the accumulated value into the output matrix C in the particular position row column. But the problem, again, is that this is not really efficient, right? Why is that? Remember that I told you before, the problem is that every time that one thread needs to access the next element of the matrix needs to go to a different cache line. So we are not really reusing the data that could be reused in these matrices, and the problem is especially bad for matrix V. So the observation here is that there are many threads that share a lot of data. So for example, the 4 threads that we assign to these 4 output elements of C, the 4 of them need to read this whole row of A, right? And also happens the same with the columns of B. So the 4 threads that are assigned to these 4 elements of C have to read the whole column, the same column of B. So the idea is to use tiling, because it's very unlikely in the GPU that we can hit in the L1 cache. This it's as I said, unlikely, because even though, you know, cache is great, it's managed by the hardware, we as a programmers don't have to worry so much about them. But the problem of the L1 cache is that it is pretty small for the amount of threads that we have running on each individual core. So the problem there is that it's very unlikely that we have one thread hitting on one cache line that was previously loaded, because most likely this cache line has been evicted from L1. So that's why it's better to have full control on what we load into the on-chip memories, and this is why we use shared memory. We could also do tiling in registers, and actually it's a, let's say, it's like the next optimization in matrix multiplication, but for today we are only going to focus on tiling in shared memory and not in registers. So what we do is same as we did in the example of image processing, is dividing the output matrix into tiles and assigning each of these tiles to the to one thread block. So here we will have one thread block computing on these 16 elements, 4x4 elements that we have here, another thread block here, another one here, and this green is like the one we are focused on. So here we have a 4x4 thread block computing these 16 elements of the output matrix C. And in the tile multiplication, the first thing that we will have to do is loading this tile of matrix A into the shared memory, and this other tile of matrix B into the shared memory, and then have the threads reading input values from A and from A and B from shared memory, which is going to be faster. So this is our first step, is loading the tiles into shared memory, and then performing the multiplication of these tiles and storing the partial results somewhere in this tile of C. And then we repeat after performing the computation for the first tiles, then we go to the next tiles, this one here and this one here, and then the next tiles, and so on. And finally, this is our code. It's like the code for tile matrix multiplication. You can actually compare this code to the one that I showed before. The main difference is that now we are loading the tile to shared memory and computing directly from reading the data from A and B from the arrays that we store, that we allocated in shared memory. But again, we need to use row and call, same way we calculated before, to access the element of the matrices of the matrix C that has been assigned to each individual thread. Notice how here we declare the arrays in shared memory with the shared qualifier and defining what's the exact size of the tiles. This tile beam is a constant. So this is kind of a static allocation. There is also a way of doing a dynamic allocation of shared memory, but it's not so relevant for today's lecture. And then after doing the allocation, we'll have to go tile by tile, loading tiles to shared memory, one tile of A, one tile of B, and then we synchronize to make sure that all threads that belong to the same thread block that it's computing as on a specific tile, all threads have done their part of loading, different elements of the tiles to the shared memory. So then we synchronize, and then we can perform the computation. And after having done the computation, we have to synchronize again. Why do we have to synchronize? Because observe that there is a for loop here. So if we don't synchronize, what may happen is that some warp will finish earlier than others. So we'll go to the beginning of the for loop and start loading the next tile into shared memory. And this will definitely produce some wrong results, because while we have, let's say, warp 0 loading a new tile to shared memory, we may have another warp, let's say warp 1, is still computing for the previous tile, but now reading values that have been overwritten by warp 0, right? So this is why we have to synchronize before and after this inner loop, where we perform the partial matrix multiplication of these submatrices or tiles. And if you want to learn more about the tile matrix multiplication, I would recommend you this part of one lecture I gave 4 years ago, and where I explain in a different way this tile matrix multiplication. What you have already seen is like the basic of the most optimized methods and most optimized kernels to perform matrix multiplication, which is a incredibly important operation these days, because as you may know, many neural networks, especially for training, use matrix multiplication to perform in a more efficient manner in architectures similar to GPUs or other architectures like systolic arrays, for example, Google TPUs, etc. If you want to read more as well, to learn more as well, you can go to chapter 4 of the book, Programming Massively Parallel Processors. And this is all for now regarding the GPU memory hierarchy. I hope that all of it was clear today. It took more or less 1 hour. If you guys have any questions, please go ahead and ask. We can review whatever is needed and clarify anything. Are there any questions in Zoom? I don't see any questions in YouTube either, so I hope that everything was clear and people found this lecture useful.
I have a short question.
Yeah, go ahead, please.
On slides 22,
Mm-hmm.
In the table, the int local array.
Yes.
Why exactly is it global in the memory?
Yeah, let me go to the exact. You mean this local array?
Exactly, yeah.
Yeah, so these local arrays, as you see here, is in the scope of a thread. So it's actually private to a thread, right? But you are giving, I mean, in the end, this is, you're completely free to declare whatever array you want to declare. And you may be declaring, I don't know, one array of 1 million elements per thread, which means that you're going to occupy a lot of memory space, right? If you have 1 million elements per thread, for sure you cannot fit that in some on-chip memory space. So the default operation, what the compiler does here by default, is placing these local arrays into the global memory, into the device memory. Why is that? Because we have several gigabytes there. So we should have another space for whatever size of the arrays that the threads need. But as I said, if this is not so big, the compiler will try to allocate these in registers, because that's going to be much more efficient and much faster access.
Okay, thanks.
Yeah, you're welcome. Any other questions? Okay. If there are no other questions, then I just want to, I can thank you for attending, and I wish you have a very nice weekend, and I hope to see you in the next lecture next Thursday, 7 p.m.